Final day of Advent of Code. We got pretty much every single day except for day 10, part 2. So it's time for the final day. Let's see how we perform. Let's get straight into it. Christmas Tree Farm. You're almost out of time, but there can't be much left to decorate. Although there are no stairs, elevators, escalators, tunnels, chutes, teleporters, fire poles, or conduits here that would take you deeper into the North Pole base, there is a ventilation duct you jumped in. After bumping around for a few minutes, you emerge into a large, well-lit cavern full of Christmas trees. There are a few elves here frantically decorating before the deadline. They think they'll be able to finish most of the work, but the one thing they're worried about is the presents. For all the young elves that live here at the North Pole, it's an ancient tradition to put the presents under the trees, but the elves are worried they won't fit. The presents come in a few standard but very weird shapes. The shapes and the regions into which they need to fit are all measured in standard units to be aesthetically pleasing. The presents need to be placed into the regions in a way that follows a standardized two-dimensional unit grid. You also can't stack presents. As always, the elves have a summary of the situation, your puzzle input. First, it contains a list of the present shapes. Second, it contains the size of the region under each tree and a list of the number of presents of each shape that need to fit into that region. Okay? Okay, I see. So the first section lists the standard present shape. For convenience, each shape starts with its index and a colon. Then the shape is displayed visually. Okay, so this is the shape of 0. This is the shape of 1. This is the shape of 2. Oh, we're probably going to have to make them fit under the tree in a weird way. Allison, what's up? The first section lists the standard presents. The first section lists the standard present shapes. Each shape starts with an index and a colon, then the shape is displayed visually, where hashtag is part of the shape and dot is not. The second lists the regions under the trees. Each line starts with the width and length of the region. So it's 4 by 4. 12 by 5 means it's 12 units wide and 5 units long. The rest of the line describes the presents that need to fit into that region by listing the quantity of each shape of present. 101032 means that you need to fit one present with shape index 0. No presents with index 1. One present with index 2. No presents with index 3. 3 presents with index 4. Okay. Yeah, this is like arithmetic. Presents can be rotated, flipped as necessary to make them fit in the available space, but they have to always be placed perfectly on the grid. Shapes can't overlap. That is the hashtag part from two different presents can't go in the same place on the grid, but they can fit together. That is okay. It's like Tetris. The elves need to know how many of the regions can fit the presents listed. In the above example, there are 6 unique present shapes and 3 regions. The first region is ... Okay. In it, we need to determine whether you can fit 2 presents that have shape index 4. Yeah. Yeah, you can fit 2 with index 4. What is this? 3 down. Yeah, you can do like this too. Yeah. After some experimentation, it turns out that you can fit both presents. Yeah, the second region is 12 by 5. It's 12 units wide and 5 units long. In that region, you need to try to fit one present with the shape 0, one present with shape index 2, two presents with shape index 4. Twelve five. Okay. Man, like, let's see. Let's look at the input. This is the input. This is a pretty interesting question. I feel like it's just like a one way to brute force it is just using like a backtracking algorithm and literally brute force. So in a 4 by 4 grid, you have 1, 2, 3, 0, 1, 2, 3. Then we need to fit 0, 1, 2, 3, 4. This twice. So one way to do it is like have this. How big is the actual data? Yeah, we can see if we could brute force it. Ooh. 50. Oh no. Yeah, you can't really. I don't know if you can. Because we have to put 51 of these. Does it have to fit perfectly on the floor? Yeah, I don't know if you could actually brute force it. Let's see the rules for how it fits the region. The L's need to know how many of these regions can fit the presents listed. In the example, there's 6 unique and 3 regions. Okay, we're saying. Okay, the second list of regions under the tree. Each starts with, yeah. The rest describes the present that needs to fit into it. Okay. 3 represents presents can be rotated and flipped as necessary to make them fit in the video, but they have to always be placed perfectly on the grid. Okay. Shapes can't overlap. That is, yeah, but they can fit together. That is, the dot part in a present shape diagram does not block another present from occupying that space on the grid. Hmm. The L's need to know how many of the regions can fit the presents listed. In the above example, there are 6 unique presents and 3 regions. Okay, let's think about this a bit. I think solution 1 is just brute force it. Like literally for every single shape, find the possible. Like we know that we need to place. So for example, shape index 4. We need to place two of these. So we could just, one way to brute force is we're gonna like try for every cell and every try for every cell and every orientation. For every shape, try for every cell and every orientation. It's like this. So we'll just try to put like one, and then now we place it, we can like mark the cell. But we only have 5 cells, or we only have 5 of these. 5. Try for every cell and every orientation. So we know we need to place 2 for sure, because we just need to fit one additional. Yeah, like one way is try for every shape, try every cell and every orientation. It's like, and we backtrack. True if we get to a result. So suppose we have like, oh, the input gets large because we have 46 by 43. So we have 36 places to put this, times 32 to place this. Let me do some math. Like worst case times. Let's do a calculator. Oh, wait. Billions? No, I don't work on ads. Why? What is that? Billions? 100,000, 100 million, 100 billion. Yo, that's gonna take forever. Yeah, I guess we can just like look at the shapes. I guess it has to hit the floor though, does it? Or can they like be floating? No, shape 4 can be fitted with shape 3. Look if you put 3 there. Shape 4 could be fitted with 5. Yeah, you're right. 2, 4. Because then it will use up less space. Because if you have like 4s and if you have multiple 4s, it'll take up space. Yeah, you're right. That's a good insight. That's a good insight. So 4 could only be fit with 4 optimally. Because if you put anything else there, like what happens when you fit 4 and 4? It takes up 2 space. Okay, but like, I mean, what if I fit this one in, like, if I do. Rotate this. I guess you can figure out which ones go optimally. Like, you could just, like, figure out how you can combine all of these. Maybe if you could, maybe all of them, like, the way to optimize is you combined it with itself. Like, maybe that's like one insight that we can make. Like, the best way to optimize it is if you combined it with itself. But then this uses up too many corners. Like here. Yeah, but can we use that insight? Yo, Zero, what up? It's crazy. Because I think, yeah, maybe if we know like how to pair them up optimally, we can just figure out like how many cells there are, and then we could figure out like how many cells get reduced every time we like join them up, and then we just need to like backtrack on that or how we fit them together. Or we just need to like do a algorithm to like match these together. Maybe we could be like 0 and make it fit in with 3. Like we can make them. Let's work on a small case. Like for this initial case, we have 4 by 4. And we know we need to fit 2 and 2 twice. Let's go back here. Let's delete this. And we know we need to, suppose this is the one we're looking for. So we need to fit 2 and 2 twice. What are the different ways that we can fit like the 4 by 4? We can use 4 by 4 like this. Or let's just like look at the different options. Like we have 4 by 4. What are the different ways? We can make them fit like this. This variation 1. And that literally takes up 1, 2, 3, 4, 5. This literally takes up 3 by 3 by 1, 2, 3 by 6. 18. We just want to minimize. So it's like, if this is like apart, or we could join them. I think we're getting onto something here. Dude, what the hell? We can join them like this. Like, what's the total geometry here? This just takes up 3, 4. Realistically, we can't fit nothing there no more. We can fit this other. We can fit something else right here though. What are like the other options? We can just, we can have them sideways like this. This 3 by 6 also. We could also just stack them. Takes up 3 by 6 as well. So basically, you can tell, you can know how much space you need at least. You need at least 3 by 6. If so, if you have like two, what if you add a fourth? What if you add a third? If you add a third, you could only get this. Like if you stack it here or stack it in this corner, it's gonna make things worse. So I think like you need to compact them, and then like the rotation doesn't even matter because you can just compact them like this. Like you just need to figure out how to pack them as much as possible. Yeah. Like what's the largest square you can get? I think all of them are 6 by 6. One, two. All of them are 6 by 6. That's one thing to note. All of them are 6 by 6. So I think we really need to only care in 6 by 6 slots. Yeah, you're right. That's a good idea. Oh, sorry. 3 by 3. 3 by 3 slots. Cause these are only three. Or I mean 6 by 6, cause I mean like we're gonna combine them, right? Like this one is like. Like it doesn't really make sense to fit any of them like right there. It makes more sense to like stack them together. Like would it make sense to like they all just partner up with the one that minimizes them, then we all just squish them together? We can get the difference between sum of all numbers and 6. Sorry, what do you mean by that? No, bro. Bro, there's like some. Yeah. Yo, Paul, we need some help. That kind of makes sense. Yo, Paul, I'll show you the problem. Essentially, we're gonna be given like the problem is pretty simple. This is like the input statement. We're gonna be given a bunch of shapes. Let's see. Me and Igo have been making some good progress on this, but like essentially we're gonna be given a bunch of shapes, and then we need to return like true or false for every single like grid that could actually fit all of these shapes. So this one, so each element here is telling you like how many of these shapes do we need to fit. So for this one, we need to try to fit 2 of 4, right? So the way to in a 4 by 4 grid, this in a 12 by 5 grid, we need to fit 1 of shape 0, 1 of shape 2, 1 of shape 4, and or sorry, 2 of shape 4 and 2 of shape 5. So we need to try to fit that in a 12 by 5 grid, and we essentially just need to count up how many times, like for how many rows you could actually fit the shapes into that size of a matrix. Does that make sense? You can get the difference between sum of all numbers and 6. Yeah, base. I don't know what that is. Okay. What is that equation gonna do? Yeah, trauma knows. Yo, yeah, this is it. But they just give you like 5 specific shapes. Yo, XVZ or XVX. What's up, man? Yeah, it was nice to see you too. Yo, this question is hard. Yeah, it's definitely some. Yeah, it's like a combinatorial problem. That makes sense. What the hell? Yo, I go. So what were you thinking of? Like, you can fit the different shape 0 to 7 numbers. Dude, yeah, I don't know. What's domino? Oh, okay, I see. I think there's like, ooh, dude, ours is like 6. I've seen a question like this before. Okay. It's not looking good. Not looking good at all. And 6. Damn. This is definitely on my tax bracket right now. Are you talking about the actual shape? 1 and 3? Like 1 and 3 here? Okay, I see. I see what you're saying. So you're saying from this set? Okay. What's the best way? Okay, the best way to fit this is this. Your input looks different? Oh, so they just can't copy you, huh? Three by five. Then what? This is difficult. If you move it up here, it takes more space. It's like a greedy. This one takes 12 space. But maybe you can figure out like what's the smallest way you can. Let's just work on small example. Like if they give you two, if they just give you any two shapes. Two shapes. What's the smallest grid? How would we be able to define that? Well, for each one, we just need to pre-calculate. Like, what's the smallest if I have two of these? If I have... Maybe it's like a top-down DP. Or like bottoms up. Because if I have a 0, right? I know that I could ask myself, if I have a O, what's the smallest size that I can fit with a O? Then I'll be able to answer that for sure. It's literally 3 by 3. If I add another O, like for all of these, if it's just by itself, the minimum is 3 by 3. You need 3 by 3 space left. But what if you start adding? What if you go like... What if you go 0 and 1? What if you add 0 and 1? Bro, this is hard. What if you add 0 and 1? What's the smallest now? Why would you let GPT parse the input? What do you mean by let it parse the input? So all by itself there, but what if it's like 0 tied? We could try 0 with like all of the different ones. Oh, you can use GPT all you want, honestly. I'm not gonna use it for this time, but maybe you can just pre-compute. So what's the smallest that you can add zero? Like if I had a 0 and 1, what's the smallest I can make it fit? Like what's the smallest? Like what area is the smallest area I can make it fit in? Probably just side by side like this. Yeah, yeah. So it's gonna be 3 by 6 or 6 by 3. It doesn't really even matter. Like 0 and 1. Wait, why does my 0 look like that? Oh, okay, I stretched it. I think with 0, yeah. Because if you try to like place it here though. Bro, I don't even know. Paul, what are you thinking? Like what are some of the approaches? What, and then you just try to force it? You think? Damn. Okay, wait. Let me take a break quick. Let me write down some of the approaches I'm thinking. So brute force it. Backtrack on every shape. Try every cell and orientation. But like I multiplied this out and there's way too many options. Or I guess do you need to do it on every cell? If you could reduce the amount on every cell. Less. Well, I guess yeah, we could just try every cell in every orientation in every order, and then we try to see how many like cells that takes up, and then we try to see if like we can fit that into the matrix. Like how many different combinations? Then could we even simplify it by saying like certain ones fit with the other ones better, so we just use that? Because we just think of like packing them all in. Well, we can like I'm wondering if like what if we could just think of packing them in just one line, and then like the rectangle doesn't really matter. We'll figure that out after. First, we'll figure out like what's the most that we can fit them in like one line like this, and then we could try to get it into the shape after. Paul, does that make sense? Or I go like literally just try to pack them all here, and after make them fit. Like depending, we'll be like, okay. I guess they really go by threes, and then sometimes like this might be four. What to do? Man, this question is way too difficult. Yo, Alpha, it's so hard. This question is difficult. Man, yo, I'll explain it to you and you're gonna be like, you might I feel like I seen it in leak code, but let's see. He got pipped where? What company? Yo, Alpha, essentially what we do is like we have all these different shapes, similar to Tetris. All the shapes are 3 by 3. And then each shape has a label. So this is shape 0, this is shape 1, this is shape 2, this is shape 3, this is shape 4, this is shape 5, right? So we just need to see that given a 4 by 4 grid, can we fit two of shape 0, 1, 0, 1, 2, 3, 4? Can we fit two of shape 4 in a 4 by 4 grid? I see. Yo, M, what company is your friend working for? So we just need to see like how many of these shapes can we fit under in a 12 by 5? Like if it's even possible to fit them in a 12 by 5. So this is like 1 of shape 0, 0 of shape 1, 1 of shape 2, 0 of shape 3, 2 of shape 4. I see. Damn, they got pipped at Bite Dance. So these are all shape, right? All shapes. So this is like just telling us try to fit the like 2 of shape 4 in a 4 by 4 grid. So it's possible because you can like if you have 2 of shape 4, you could just make it fit like this. That's literally what they said. You got to get more kit. Try to fit one present. Yeah, it's so weird. So my initial like one of the my brute force is if you had unlimited time, you could literally just brute force it, backtrack it for every shape, try for every cell and every orientation. So you just like try to place it and you just backtrack all the way, and then until you could see if you're able to place every single shape that you need to do, right? But that just leads to like millions of combination. Like just that's the brute force. Can you just place them? Yeah, for this one, Alpha, take a look at this one. For the third region, 12 by 5, you have to fit like all of these shapes in there and then you can get this shape. And look at the way that you have to fit it here though. It's so weird. Yeah, I can't figure I literally can't. I guess the question is pretty much asking given X blocks. It's like a packing problem. Dude, I'll do C plus I'll learn C plus plus next year probably. Given blocks, can you make them fit in a grid? It's like a packing problem. Optimal packing, pause. Igo is like making some good progress on it. Dude, there's like a Paul, what are you thinking for this? You got any suggestions? Or are you lost as well? Why do the AI labs want Rust devs? What's your question? What do you mean precalc all rotations? Okay. This was my initial thought. Paul, are you pretty much saying this? How do you? So what's your logic for? Let's see your code. Send me your code. Send me your code. How did you try to place it? You'll send it in the Discord. Listen. So it's just a brute force. Damn. This one's rough. This one is rough. Let me call this guy on Discord. Nah, he might be doing something. Shabash, what up? Hell nah. Why don't you just send it to me on? Like, break it down. My God. Shit. When you place a piece, how do you figure out how much space it took? Sort pieces by size. Try to fit out in the grid using backtracking. What the hell? This is cooked. What the? Let's just, let's just run this on your. Where do you read the input? Yeah, I got cooked. I can't. Let's go. Pause the goat. Pause the goat. I'm not claiming that though. I need to look that up. Part 2. The elves thank you profusely for the help and start rearranging the oddly shaped presents. As you look up, you notice that a lot more elves have arrived here at the Christmas tree farm. In fact, many of these new arrivals look familiar. They're the elves you helped while decorating the North Pole base. Right on schedule, each group seems to have brought a star to put atop one of the Christmas trees. Before any of them can find a ladder, a particularly large Christmas tree suddenly flashes brightly when a large star magically appears above it. As your eyes readjust, you think you notice a poorly man with a white beard. You go only 23 stars to go. What? Paul's a legend, man. I need to look. I need to look up that. The elves thank you profusely for the help and start rearranging the oddly shaped presents. As you look up, you notice that a lot more elves. As you look up, you notice that a lot more elves have arrived here at the Christmas tree farm. In fact, many of these new arrivals look familiar. They're the elves you helped find a ladder. A particular large Christmas tree suddenly flashes brightly with a large star magically appearing above it. What is it asking? Oh, it's not even asking nothing. There's no part 2, really? Damn. Yo, chat. We did it together. With Paul's help, with everyone on the chat. That was depressing. Yo, wait. Walk me through this. Thanks, Shabash. Build the list of pieces to fit each piece. Variations times count. Sort pieces by SARS. Size by SARS largest first. Does this way work always? Oh, I need to finish. Oh, I need to finish all the. Okay, okay, okay. I tripped out. Okay. Bro, this is so annoying. Like, I had it. Yeah, I got cooked on day 12. Bad performance. Terrible performance. Thanks, Paul, for getting me on that, though. Ramen, what's up? Were you able to solve it?